Ohayou gozaimasu. I'm Jaylin. So I'm from EMQ, and we joined the Agile organization last year, but I didn't prepare the slide of self-introduction here. Yeah, I believe the good project, the good open source, speaks for itself. Okay, so I have to delete a certain of my content here because I just realized that this is a 30 minutes talk, not 14 minutes. So we are focusing on the AI fuzzing framework today, but skip a certain part of the in-vehicle AI agent. So with the help of the AI fuzzing, I believe it can help us achieve the better and safe security and safety in the SDV. So I have structured today's session around 5 core concepts here, inspired by the profound engineering culture here in Japan. So we will move from the keihatsu, our awakening to the problem, to the henka, the rapid change and the quality speed dilemma it brings. Then it's jisen, putting AI in loop fuzzing into practice. Then to the kaizen, so continuous integration in the, with the SODIF data closed loop. And finally, to the QSO, co-creation with our open source ecosystem. So actually, this is the following talk of my session in the last year of Open Source Summit Japan. So I delivered a session about our one of our failure in the production scenarios, and the lesson we learned from that, and we would like to try to amplify FTA with the AI fuzzing technology. A friend from MTA MediaTek come to me, ask about is that product already released? So nowadays we are here to present this most updated stage of this AI fuzzing tool. So let's start with the awakening, keihatsu. So let's recall where we are now today. So this slide distills the core insights from Murata-san's keynote last year in the same room, which define the 3 foundational pillars of the SDV. They are software first architecture, continuous software evolution and iterations at the consumer pace. So and he also suggests that to maintain a single software baseline and unify all car models. So this, surprisingly, this is exactly what we did in our production case, and we are benefiting from it a lot. So every failure, every case we encountered in the production scenarios make our product stronger, and it massively reduce a lot of maintenance cost. So Murata-san's insight echoes here. What a coincidence. So, and back to our topic here. So I believe this insight immediately surfaced the most critical question for everyone. How do we guarantee the software quality while moving fast? So Murata-san posed what I believe is the single most important question for SDV era today. He asked about how do you design the software SDV software first, where you continuously I need to repeat this. While continuously update and improve the software after SOP, while ensuring the quality that automotive requires and without blowing up the OEM's R&D cycle. So the insight echoes 3 massive tensions, and we are feeling it too. Yeah, first, the tension between the software first speed and the OEM certification process. We want continuous delivery, but most of the QA processes were designed for 3, even 5 years hardware cycles. Second, the second is the tension between the post-SOP evolution and the safety standards. So in the past, software was frozen at the start of production, but today, every OT update is a potential regression. Yet regulations apply to every single patch. Yeah. So it leads to the third one, the tension between the supplier ecosystem and the vertical software control. So the legal legacy LEMs relies on the hundreds of suppliers. Yeah, just Honda just clarified. So we are also one of them. While newcomers like Tesla, they own the full software stack. So how do we overcome their competitive advantage? Okay, this brings us to the chapter 2, the handicap. So the change and the quality speed dilemma. So our industry faces a massive speed gap. The closed loop systems from example like Tesla, they can deploy OT updates in 72 hours, while other traditional OEMs takes 90 days, even more, because they rely on the supplier's pace. So why? I believe the most obviously issue is the manual testing cannot scale to 600 million lines of software stacks. So traditional tools failed at the deep, stateful protocols and applications in the vehicle. So meanwhile, and the regulations also demand the continuous compliance evidence for every patch. So we're really caught in this deep quality speed dilemma. So generating static documents is not enough. We need to have a dynamically verifying verifying tools for security and safety. To resolve this, I believe we need a fundamental shift in how we test. So we realize throwing human testers, engineers at this problem wouldn't work. So this is also like lesson what we learned before. It's pretty exhausted. So before we dive into our solution, I need to briefly explain the fuzzing and AI for maybe some friends not familiar with. So think of fuzzing like a simulation framework or your stress test tool for your software. So after all, the software runs in your car. It's just deal with the input-output bytes or byte strings. So the fuzzing is feeding it with massive amounts of random malformed data to see if it crashes or behaves unexpectedly. So it's a critical tool for uncovering hidden vulnerabilities. And recently, we have seen a massive shift in how effective we have seen a massive shift in how effective this could be. So take Anthropic as an example. So they discovered a 27-year-old zero-day bugs in heavily audited open source project like OpenBSD. So it realized and it discovered that the traditional fuzzers, ran millions of times on those code bases and project and found nothing. So but AI can find it automatically because it understood the semantics of the code. It's not just produce random byte string to test your software. Okay, so I believe this is an inevitable trending of the future of cybersecurity. Then you can look back to our roadmap. So we started this initiative at 2024, and we started it as a MQTT fuzzing research project. We launched it as a joint project with university in Hong Kong, Hong Kong Polytechnic University. Then, and now today, it becomes the first end-to-end framework connecting your static documentation analysis with the AI seed generations and the runtime semantic feedback. So we are trying to combining your ISO 26262 and SPICE engineering directly with the dynamic AI fuzzing. Okay, let's enter our third chapter, GSEN. So we are being requested by the customer to do FTA analysis before, and let's look at this the engineer in the screen. So this is a traditional manual challenge of functional safety. A human engineer manually tracing the exponentially exploding fault tree analysis is even harder if you got 6 million, even more lines of code. And it faces human limitations. It scales poorly, and it leaves incomplete coverage. And now, we can have AI as our assistant. So this is AI-enabled solution. So we use AI agent for smart mutation and test data generation, combined with the data we collect from real production vehicle. So ingest your architecture modeling descriptions like your UML or system ML, and your real-world vehicle data packets captured. Then AI agent can systematically navigating your FTA tree, to find discover those ignoring bug and uncover code paths. So we have added also some specific extension for automotive industry as well. Now, but here I need to elaborate a bit more about this last option here. So what is Oracle DSL? So think of this way. The traditional testing only flags an error if the software completely crashes, like memory, outbound, or segmentation fault. But in a car, the software might not just crash at all. Instead, it might smoothly and flawlessly execute a command to open the door or pass the vulnerability to the next module, which leads to a vulnerability in whole vehicle, in system wheel. So this is also the exact problem we got in our production case. Yeah. So I believe then I realized that we have to have a human set limitation or discover rules for AI to use it as a policy guard or feedback rules. So, but why is the proto fuzzing or SDV fuzzing so hard to begin with? So why do we need this complex AI framework? So it all comes down to what we call the deep state problem. Yeah. Also, the traditional testing methodology fails. Why they may fail, or partially failed. So imagine trying to break into a high security bank. The traditional fuzzers fail for simply 3 reasons. First, the message grammar. Yeah, like your API input parameters. If a fuzzer breaks the basic framing of a network packet, the shallow parsers, the front gate, or your the simple if-else conditions, just reject it immediately. You learn the testing framework learn nothing. So about what's inside, so it's the second one, the session state. So protocols and SDV applications are stateful. Most of them are stateful. So you cannot request the sensitive data without first authenticating. So a fuzzer without the session context gonna waste 80% of your testing time and being rejected for the first condition in your code. So the third one is protocol transactions. So think of it as a UDS security access. So you request the seed, you must respond with a key within a strict time window. And the blind mutation cannot orchestrate with these limitations. So our key insight was the bugs that truly matters, that are hard to find, the one that causes sudden black screen or allow the remote attack on your vehicle, are invisible to the tools that only look at the basic response codes. So you need a deep semantic awareness. And that is exactly what our fuzzing framework trying to deliver. So as you can see this in the diagram, it consists of 3 stages. The first one is static target preparation. We're trying to combine, work with the static documentation workflow. But I'm not an expert on the documentation and on functional safety here. But we are trying to work with our customers and with our friends who are expert on this part. Stage 2 is generating the seeds, and also review it with the reply admitted mechanism to make sure the AI fuzzers goes in the correct path. The stage 3 is put AI in the loop, and that make AI can iterate it over itself to find a better path at each execution. Okay, start from this page, it's gonna be pretty technical. I will make it short. Okay, so anyone who are willing to learn from it, we can have talk later, or I will donate this project as well. So let's dive into the stage 1. So we run a dual track system. The track A is the AI track. We use the Ceylon AST to scan the entire your source code base. And the track B is the safety engineering track. We can parse your static engineering documents like ISO 26262, technical safety concept, spice design docs. So then it comes to the step 2 here, the semantic enlargement. So we map the physical code side directly to your safety requirements IDs. If your design the documents dictates something that violates your code, the system flags as a design implementation mismatch. So before we even run the code, then we assign a functional score to prioritize our testing resources. Yeah. The step 4 is the refined code chain synthesis. So this sounds highly technical, but think of it this way. We can first import a golden path from your spice docs documentation. The standards expect a sequence like operations, like a safe GPS route. Then we let AI act like a unpredictable but technically legal driver. It takes a golden path and it injects the unexpected disturbing sequences, like sending to overlapping requests before the fully authenticating. So to stop the system from drowning in the random noise, we have to extract the tail signatures of these complex paths, which records in your documentations. So this is a process we call it bucketing, bucket. So what we get is a robust, noise-free path templates. So we don't start fuzzing from zero. We have to prepare the knowledge base for it. Okay, now we take those intelligent path templates into the stage 2, the replay admitted seed generations. So we use AI acting large language model to act as a protocol expert to build the initial long prefix sequences. But we don't just want the compliant traffic. We are hunting for those vulnerability bugs. So we introduce a strict model guided mutation. It works with the materials or the template we generated in the last stage, and we feed this Terra result into the larger language model. The AI injects malicious vectors, such as session hijacking vectors or malformed topic maps. So hidden inside these perfect valid protocol envelopes. So we also extend this to sortive boundary scenarios. But this part is still in progress. Yeah, it can mimicking or pretend it as a high to build a high network latency or redundant subscriptions to trigger non-fault failures. Those kind of scenarios is hard to reproduce in your testing environment, but which is the most difficult issues in the real production. Yeah. And the third one is that we all know AI can be hallucinated. So if we feed hallucinated garbage into the fuzzers, the whole system is doomed to fail. So this is why we enforce also a compliance-based replay admission here. It will replay the seed we generated at this stage, and every single candidate seed can execute in a binary trace environment. We use either code or compiler instrumentations to use it as a feedback or tracing part to ensure the seed can run through the path we wanted. Yeah. So only those verified deep reaching seed entering our last steps. Our last step. Okay. So finally, we put in AI in the loop. We execute. So the stage 3 is we feed those high-valued, pre-verified seed into our fuzzers. Then they are but we throw away those traditional code coverage bitmaps. They are a bit too noisy for our limited human resources. So instead, we use a safety-augmented, safety-powered event map. So every time a code site, a code condition is hit, we hash the instruction ID, the semantic fact in the previous event, also including those current safety state, so into a hash map. Yeah, here. So this allows us to track the hidden paths that cause the system to silently transition from a safe state to all other abnormal or emergency state. So I believe the human engineer cannot go through all possible paths to build a complete FTA document, but AI could. AI doesn't require sleep. Yeah. So we let AI do this job. So an AI navigator continuously monitors this map to ensure itself goes into the right path, not circling in the same path. If it spots something suspected, so it flags it as for human review. If the fuzzers is wasting energy on the dead end, also human can terminate this path. And for the final audit, so we don't just capture and hard crashes using memory sanitizers. We capture it with the semantic violations using the Oracle DSL. This concept I just elaborated before. So we catch this logic bugs, and AI can capture the packets that a series packets that generated to trigger this bug. So it's easy to replay it for engineers to pinpoint the issues. Yeah. Okay. So this sound may be a little bit like a scientific fictionary, but this is true, truth, because we got a lot of we have benefited from it a lot, not only on our own AI fuzzing tools, but also with the community from all over the world. Our open source project receive a lot of security and safety researchers that contribute their insights, their findings to our GitHub repositories, and they all provide provide it with detailed reproduction proof of concept data set. So this dramatically speed up our production pace. So here you can see actual runtime status dashboard for our fuzzing engines. Currently, this is not quite easy to use. It doesn't have a fancy dashboard. But this is a two screen I captured for testing TLS library and our NanoQ project. So this records whether just a quick look at some interesting metrics here. So the corpus count is here. Yeah, it's a number of interesting test cases kept in the queue. In the queue. Yeah. So there are inputs that further decided to retain because they produce the useful feedback. So it reads the feedback for that hash map, and it will you have an agent that to directly the AI model to mutate the next sequences of byte string to discover deeply in your path. The next one is a metric called favorite. Favorite is a queue that entries that preferred by the schedulers because they cover useful feedback slots. So these inputs are usually given more mutation energies because they are considered valuable. And this is a saved crashes and saved oracles. So this, when you can see the color is different. So when these two metrics flex, you know what is really going wrong. Yeah. So saved oracles records that inputs that saved because they trigger a new oracle or semantic findings. This is violates your documentations. This is separated from the crashes. The target may continue running, but it already behaves in an unexpected way. The crash is crash. I don't need to explain more. Then the semantic slots. The number of distinct semantic feedbacks state it reached. So the semantic slot number should be as high as it could be. So it means I can discover how many paths in your code base. Okay, the Oracle slots is a number of distinct Oracle rule result slots that reached. So you define those Oracle rules from your documentation, and you can track has your fuzzing go conduct every rules as you put it to, yeah. Okay, so we have a revolutionary testing engine, but how does it fit into OEM's daily workflow? So this brings us to the chapter 4, Kaizen. So this is a continuous improvement. So we integrate this fuzzing directly into, we propose to integrate this fuzzing directly to Agile Automotive architecture here. So it can act as a security CI/CD gate. So imagine engineer commits a new piece of code of the telematics unit. Before the code is merged, a fuzzing action is triggered using Yocto meta layers. Then build artifacts are auto instrumented with the help of your static documentations. Then engine runs the target semantic guided fuzzing campaign. It may run several hours. If the memory safety bug or protocol correctness violation is found, the deployment is blocked. So I believe this could answer Murata-san's question in a certain extent. Yeah, we guarantee the quality at the speed iterations. And as a byproduct, maybe we can explore a CI to run as auto-generators for your ISO 21434 proof, even the UNR 155 coverage report. Maybe this architecture shows a familiar view for you guys. So you can, so one part is we need real vehicle data collection. So our project donated to the Agile sits as a Dong.io gateway here. It collects data for AI to use it as a knowledge base. Okay, so this brings us to our final chapter. Yeah, QSO. How many times? I'm going too fast. Okay. So, but to make this truly powerful across the industry, we must address the cultural issue here, the data transparency. So the foundation of SDV safety is data-driven. And right now, silos are killing automotive safety. But currently, each OEM rediscovers the same protocol level bugs from our perspective. So furthermore, we can share this collective data for AI training. Even hardening the defect datasets, which means our community's AI tools can train on shared production failure modes. So this could create a flywheel effect. More shared data leads to better AI seeds for AI fuzzing. Yeah. Better seeds finds more bugs. More bugs finds leads to a better safety. Yeah. Okay. From this page, it starts the AI agent, in-vehicle AI agent chapter, but we don't have enough time for this then. We'll just give a quick end here. So where does this ultimate data come from? So this part was beginning of the vehicle AI agent. Yeah. So we donated Willow RT and Willow Flux to Agile for signal capture and pre-labeling of the signal stream. So we capture the real vehicle signals and pre-label it, and the data is transmitted to a cloud for AI fuzzers to synthesize with it. Yeah. Okay. We don't have time. Okay. I believe I can call on everyone here as we can work on this together. I plan to also donate this prototype of AI fuzzing framework to either Elisa or Agile, and we can build it together and using production data to run shadow mode AI diagnostics. Yeah, the bug of tomorrow are in our code today. let's find and learn together. Yeah. Let's thank you very much. Arigatou gozaimasu.
Yeah, thanks, kind of sharing with this interesting topic. Yeah, when I listen to this kind of the story you make, right? I'm trying to be a lot of stuff not familiar to me. Can you kind of give me kind of intuition, right? What is essentially, all these kind of large language model, right? What is trying to be kind of challenging you try to tackle in the first principle? So so I can establish some intuition.
So this is most common challenge elaborated in this AI-generated picture.
It is still kind of a little bit complex for me. Right? Is it something you try to use in large language model to help you to do the FTA, fault trees analysis?
Yeah.
In a simple tone.
Yeah, this is the beginning, very beginning of our initiative. Yeah,
okay.
I found it pretty human exhausting and resource hungry, and you need to go through the millions of lines of code to sort it out as FDA documentations. However, I believe it's more easier for AI to navigating in your code to find the correct path. Yeah, not the correct path, find all paths. Yeah, but human can make a mistake.
But think about it, I have further questions on this, right? FDA is looking for kind of a static code path analysis, right? Try to identify exhaust, right?
Yeah.
Statically, in a compiling time, to identify, right, the latency of each possible branch, right? This need to be deterministic. But how you can be expecting a large language model, this kind of it's not deterministic, so to help you to.
You're asking about deployment, right?
I'm asking about this kind of a little bit contradicting kind of methodology, right? Try to solving something like using non-deterministic kind of path, right? To solving some deterministic problem. How you fill up that gap?
Oh, you mean deterministic and
non-deterministic path, because large language model is non-deterministic path. To solving the FTA, right? This is looking for deterministic.
So human are also non-deterministic. AI is also non-deterministic. But we human is trying to build a deterministic FTA or deterministic architecture. So AI is just taking this job. It's not compulsory for a deterministic tool to build a non-deterministic tool to build a deterministic architecture, and AI can do a better job than humans. Yeah.
I see.
Okay. You guys can talk about it later.
Yeah. Thanks, kind of sharing with us.
Thank you.